We're now starting the final chapter of Algebra 2 plus Trig Honors, which is on Chapter 12, Conic Sections. This is where we start deviating primarily into a pre-calc context, but this does have some direct connection and ramifications from our Algebra 2 curriculum that we've learned thus far. So the first thing on this section on conic sections is, what the heck is a conic section? Well, a conic section is a curve obtained as the intersection of the surface of a cone with a plane. So if you have two cones, as is shown in the video right now, pointed with their tips facing each other, and then you took a slice through it, the cross section of that slice, that is what we call a conic section. So let me give you another visual example. So what we're going to be doing today is, if we took a horizontal slice, perfectly horizontal, the cross section would be that of a circle. This is a shape that we are familiar with. Now if we take a slightly more of a diagonal cut, we're going to get a different shape, but for right now we're going to focus on what happens if our slice is really diagonal, and we're going to get a shape that we're familiar with, which we're going to cover in 12.02, which is the parabola. But if you take a little bit less of a diagonal slice, then we're going to get something that's called an ellipse. An ellipse is an oval, but it has more mathematical technical definitions and ramifications from that. And then finally, if we take much more of a vertical slice, then you're going to get the last conic section, which is called a hyperbola. All four of these shapes have different rules and approaches, but also different ramifications and extensions and practical applications, which we will be going over in this chapter. But before we dive into it, there's going to be a decent amount of graphing in this chapter, so I want to make sure that we are well aware and familiar with the old properties that we learned in previous sections and previous chapters of Algebra 2. Now if I look at problem number 1, I have f of x equals the absolute value of the quantity x minus 3 quantity absolute plus 5. And if you remember back when we were graphing, way back in the beginning of the year, we learned that that minus 3 component, that shifts us right 3 units, and the plus 5, because it's on the outside of the parentheses, that's going to shift us up 5. So if we wanted to graph this, if you took the parent function, which I have on the graph already, all I have to do is I have to take this parent function, shift it right 1, 2, 3, and then up 1, 2, 3, 4, 5, and that would produce the graph that we're looking for in this problem. Problem number 2, similar approach. I have g of x is equal to the quantity of x plus 1 quantity squared minus 4. That minus 1 that's inside the parentheses, that's going to shift us left 1, because when it's inside the parentheses we do the opposite. But then when it's on the outside the parentheses, like the minus 4, that's going to shift us down 4, because when it's on the outside the parentheses, it does exactly what we think. Negative moves down, positive moves up. So all I'm going to do is I'm going to take the parent function, which I have right here, and I'm going to shift it left 1 and then down 1, 2, 3, 4. And this is what the graph of g of x would look like. And then finally, problem number 3, I want to throw an exponential in there because those are the ones that tend to mess people up. If we look at the exponential, we might notice next to the x, there is no minus 3 or plus 1 like there is in problem number 1 and 2. That means for this problem, we're not actually going to be shifting left or right at all. If you wanted to imagine it as a minus 0 to help you, we're not going to move. But that minus 8 at the very end, that is going to translate us down 8. So we are going to actually take the parent function, which we have right here, and go down 8, which takes us to right here. And this is what the graph of problem number 3 would look like. So this whole shifting left, right, up, down, it's really important because we're about to deal with circles where those transformations and subsequent graphing techniques are going to be utilized for them as well. Now that we've got that out of the way, now we can start to see some connection between what we've done in the past and what we're doing now. The graphing equation that represents circles is the following. The quantity x minus h quantity squared, where h represents how you're going to move left or right, it's your horizontal shift, plus the quantity of y minus k quantity squared, where k represents your vertical shift, how you shift up and down. And that's going to be equal to r squared, where r represents the radius of the circle. So do notice it's r squared. The number that you're going to be equal to in the equation is not the radius. So if it's equal to, say, 7, that's not a circle with a radius of 7. The other thing to take note of is now we have the x component in parentheses and the y component in parentheses. That means we're actually going to be changing the direction for both. I'll show you what that means in a moment. So in my example, I have the quantity of x minus 5 quantity squared plus the quantity of y minus 3 quantity squared equals 16. Now because I have a minus 5. We're used to saying, okay, that shifts us right 5. But here's what I mean when I'm saying that the second part, the y value, is in parentheses, just like with the x. For the x value, we had to do the opposite of this. We had to make the minus 5 make us move right 5. Now this component is also in parentheses, which means we need to abide by the same rule. You need to take the y component and we need to flip it. A positive 3 is going to make us go down 3. So that's what this component does, because now we're in parentheses. And then lastly, this is what I talked about a little bit earlier, the radius of this circle is not going to be 16. The radius is the square root of that value. This radius is going to be 4. The reason the radius is 4 is because in the equation it says you are going to be equal to the radius squared. So we need to ask ourselves, what number squared is equal to the 16? Well, the way we figure out algebraically what number squared is equal to 16 is we square root, because 4 squared is equal to 16. So now we have what we need. We have how far we're going to move left and right, how far we're going to move up or down, and we know the radius of the circle. So let's start doing this. We're going to go right 5, which takes us to right here. We're going to go down 3, which takes us to right here. That means the center is going to be right here. This is the center of the circle. We mark it with an X, not a dot, because it's not a coordinate on the graph, but it is an important location. Since the radius is 4, what we are going to do from there is from our center, we are going to go up 1, 2, 3, 4, and draw a dot. From our center again, we're going to go right 1, 2, 3, 4, and draw a dot. From our center, we're going to go down 1, 2, 3, 4, and draw a dot. And from the center, left 1, 2, 3, 4, and draw a dot. And then we are going to connect those dots as best our artistic ability allows to kind of try and attempt to draw a circle. And this is the graph of the example provided. Now that we got that out of the way, let's try and speed run some of these a little bit more. So in problem number 1, I have an x plus 1. I know that shifts me left 1. I have a y minus 4. That means I'm going to be going up 4. And then I have a 9 equal to the equation. That means the radius is going to be equal to 3, the square root of 9. So we're going to go left 1, up 1, 2, 3, 4, mark that with an X, radius of 3, so we go up 1, 2, 3, right 1, 2, 3, down 1, 2, 3, left 1, 2, 3, and then there is our circle. Now before I move on to problems number 2 and 3, I do want to discuss at least the domain and range. I'm not going to require that you do this, but I do want to discuss it because it is important to start denoting what the domain and range of specific functions, or in this case non-functions, are, because later on in mathematics, naming and locating the domain and range of functions becomes very, very important. It allows you to use, or more importantly, not use specific tools and skill sets. So remember, the domain is saying, where does this function exist in the left and right direction? So it is going to exist from negative 1, 2, 3, 4. It's going to go all the way to negative 4 in the x direction. It's going to go all the way to positive 2 in the x direction. For the range, that's where it lives in the y direction. The lowest it goes is positive 1. The highest it goes is 1, 2, 3, 4, 5, 6, 7. And it includes those values, which is why I'm putting brackets. So there's my domain and range for these functions. Problem number 2. I have an x minus 7. That tells me I'm going to go right 7. Notice that the y value is all by itself. There's no parentheses around it. There's no y minus 4. That means because we're not going to be having parentheses around here, we're not adding or subtracting anything. That means we're not going to move up and we're not going to move down at all. Now, if you want to write up 0 or down 0, that's fine. But if you don't want to write anything, that's also fine. Then finally, the radius is going to be the square root of that 1, which is 1. So let's go right 1, 2, 3, 4, 5, 6, 7. Radius of 1, so up 1, right 1, down 1, left 1. Draw a circle that goes through these. And then for funsies, I'm going to list off the domain and range. Good practice. For the domain, it goes 1, 2, 3, 4, 5, 6 is the furthest to the left it exists. And the furthest to the right is 8, put brackets because it includes both of those. And then the y value, the lowest it goes is -1, the highest it goes is +1. There's our domain and range. And then finally, problem number 3. I have an x minus 6, that tells me to go right 6. I have a y plus 8, that tells me to go down 8. And then I have a 36 for my value that is equal to, the square root of that is 6. So there's my radius. So let's try this. Let's go right 1, 2, 3, 4, 5, 6. Down 1, 2, 3, 4, 5, 6, 7, 8. And you might begin to start noticing a problem that I'm going to have. Because if I go up 1, 2, 3, 4, 5, 6, and I go right 6, I don't have enough space to go right 6. But also I don't have enough space to go down 6. So I kind of have a little bit of an issue. I don't really have enough graph to go further to the right or further down. So I can either try and draw these leftover regions down here, but that's going to be really crappy because I suck at drawing. So instead, I'm going to do a different approach, which is I'm actually going to change the scale of this graph. Instead of making each one of these horizontally a jump of 1 and vertically a jump of 1 each time, I'm going to actually double it. So I'm going to make this go all the way right to 20 and all the way up to 20. So that's going to give me a little bit more wiggle room. So I'm going to go right 2, 4, 6, down 2, 4, 6, 8. This is my new center. And my radius is 6, so I'm going to go up 2, 4, 6. Going to go right 2, 4, 6. Down 2, 4, 6. Left 2, 4, 6. Draw my circle. Then let's, for funsies, state the domain and range. Domain and range is always a little bit more tricky when you start changing the scale. You do have to be mindful of that. The domain, the furthest to the left it goes is 0. The furthest to the right it goes is 2, 4, 6, 8, 10, 12. The furthest down it goes is 2, 4, 6, 8, 10, 12, 14, so -14. The furthest up it goes is -2. And there's my domain and range. The very last thing that we're going to be covering is something that's going to make this problem a tad bit more difficult, which is we've gone into these problems presuming that they're in graphing form, presuming that the x is in parentheses, and it's like x minus 3 and quantity squared. But that's not always the case. And this is, the honors section, so we got to, raise it up a difficulty. What happens if it was all multiplied out, like the problem presented in front of us right now? Well, I need to do some kind of manipulation to this to where it's something like x plus 5 squared plus y minus 3 squared equals something like a perfect square, like, I don't know, like 25. This is the format that I want. Now, the answer is not going to look like this. These are not the right numbers. But this is something that I want. And getting from something like x squared plus 6x into a perfect square, we've done something like this before in this class. We've already done this work before. The steps in order to get from an x squared plus 6x into an x plus 5 squared is the process of completing the square. The only difference between that concept and what we're doing now is we actually want an x quantity that's going to be squared and we want a y quantity that's being squared. So now we actually need to do completing the square twice over. Now the question that I often get asked when initially starting to do this is like, well, what do we do with the 22? Well, we do with the 22 exactly what we did in the previous completing the square lessons. You're going to ignore it. You're not going to deal with it. You're just going to throw it off to the side and we'll deal with it later once we've actually completed the square 2 times in this case. So first, let us look at the x squared plus 6x. If I was to draw an area model for that with the bottom right portion missing, and we're going to state that this area model is a perfect square, then this is going to give me an x squared, and then whatever's in these two boxes, they have to be combined to get that 6x. But more importantly, because it's a square, whatever's in those two boxes have to be the same quantity. Therefore, whatever in those two boxes actually have to be half of that. So it's going to be positive 3x and a positive 3x. Because, again, these have to combine to get me the 6x, and because it's a square, that also locks us into saying these have to be the same thing. Well, if these have to be the same thing and they have to combine to get 6x, that's a fancy math way of saying it's just half of this quantity. So now I know what the outside of the value of the area model is. It's x plus 3 and x plus 3, which means I need a plus 9. That's what I need. Now I'm going to do this exact same thing, but now I'm going to do it with the y values. So I'm going to do another area model with the bottom right portion missing. It's going to be y squared. Do this a little faster. Now it's negative 5y and negative 5y. Because remember, those need to combine to get to negative 10y. So that's going to be y minus 5 and y minus 5. That means the part that I'm missing is positive 25. So here's what I'm going to do. I'm going to rewrite the original equation, and I'm going to input a positive 9 and a positive 25 where I need them. So I'm going to have x squared plus 6x, and then I need a positive 9. So I'm going to go, you know what, plus 9. I'm just going to add that in there. And then the y value, I have a y squared minus 10y, and it needs a positive 25. So you know what, I'm just going to add it in there. And that plus 22, it's still chilling. But now I've kind of broken the rules of math. I can't really just throw in a plus 9 and a plus 25 into a problem unless on the same side of the equal sign, I also subtract 9 and subtract 25. Because if I add a 9 and subtract a 9, those cancel. I'm not doing anything. If I add a 25 and subtract a 25, again, they cancel. I'm not doing anything. It's still equal to 4, by the way. But I am going to use these three components and get an x plus 3 quantity squared. And I'm going to use these three components, and that's going to give me plus y minus 5 quantity squared. And then lastly, all three of these components will combine together to give me negative 12 is equal to 4. And we're nearly there. We got the hard bits done. We've got the two quantities, the x and the y, both being squared. The only last bit to tidy up is that negative 12. We don't like that there. This is not in graphing form. We need to move this to the other side. So you know what? That's exactly what we're going to do. We're going to add 12 to both sides of the equal sign to leave us with the quantity x plus 3 quantity squared plus the quantity of y minus 5 quantity squared is equal to 16. And now we have an equation we can actually graph. And it all came from us just completing the square twice. So from this, I know I'm going to be shifted left 3 and up 5. 1, 2, 3, 1, 2, 3, 4, 5. There's my center. I know the radius is going to be the square root of that 16, so it's 4. So I go up 1, 2, 3, 4. I go right 1, 2, 3, 4. I go down 1, 2, 3, 4. And I go left 1, 2, 3, 4. And now I have my four corners. Now I can, to the best of my artistic ability, try and draw a circle. And we are now done with this problem.